Hello, this is Concrete Path. This lecture is starting from the symmetric cable. We call that as symmetric cable when the load is such that it is on the horizontal length of the it's along the horizontal length L. It's along the horizontal length L, and the supports are at the same level. So in that case, the profile formed is symmetric. So we call this profile as symmetric profile. We call this profile as symmetric profile. And in this case, we say that your H1 equals to H2. But in the previous problem, we said we were solving for unsymmetric cable, that you are having two supports at different levels. Because of that, you had H1 sag, you had H2 sag, and similarly you had a length of L1 up to the point of that origin point, what we called as origin, the lowest point, and similarly from this side we had L2, and then we got those 2-3 relations. Now it's for the second case that we call this as a symmetric cable. Here the supports are at the same level. Delta elevation difference is equals to 0. So because of that, we say your profile becomes symmetric. So let's say that your H1 becomes H2 equals to H. Okay, and one more thing is that your L1 equals to L2. Your L1 equals to L2. That's we know total L1 plus L2 equals to L, and we say that L1 equals to L2 equals to L by 2. Okay, then we have the equation that dy by dx equals to, if we have the equation of standard equation of parabola, we write y equals to 4h x square by L square. And if I get the dy by dx, that slope of that dy by dx, if I write that dy by dx, I would get the slope of the cable, that parabola. So that is 8hx by L square. 8hx by L square. If I differentiate this y, I would get this 8hx by L square. 8hx by L square. And I have one equation of that. Tx. Do you know this equation? Tx equals to h times 1 plus dy by dx whole square. We had derived it in the previous lecture. T equals to h 1 plus dy by dx whole square. Then we had to get the value of h, and we had to get the value of dy by dx. And we know the value of dy by dx. Do you know the value of dy by dx? This one is your dy by dx, 8hx by L square. So if I write this as a standard equation of that tension at any x, so if I want it to be minimum and if I want it to be maximum, I had to substitute the limits where it can be maximum and where it can be minimum. So let's apply those limits. Let's apply those limits from the origin. I would say at this point your slope is 0. If your slope is 0, that means your dy by dx in this equation is 0. That means what we can say, your Tx would be equals to h itself. So your T minimum would be equals to h. So if I have this one, if I erase this part, I will show you that. I will be showing that. So I would say at x equals to 0, if I substitute the limit that when the x equals to 0, that means when x is at this point, so at the origin itself, when x is 0, at that location we say your dy by dx is 0. At that location dy by dx is 0 at the location of x equals to 0. Then if I substitute that value here, I would say tx is equals to s times 1 plus dy by dx is 0. So finally I would get T minimum equals to h. T minimum is equals to h, value of h, horizontal. Now I want to get the value of T as to be maximum. So for that, dy by dx is to be maximum. And where we can get a dy by dx maximum? And if I substitute that at x equals to L by 2, or I can go minus L by 2 also, then there I have that dy by dx maximum there. We have there dy by dx maximum, slope is maximum there. So I can substitute that value, that x equals to L by 2. If I substitute here x equals to L by 2, I would get the value that let's have that value. I would write at x equals to L by 2, your your value of what's your value of let's substitute that value, h times 1 plus 8 into h into L by 2 divided by L square and whole square. Can you get the value here? What's the total value here? What's the total value we can have from this one? I would say this is 1 plus 8 8s are 64, and it's h square, it's L square divided by 2 to the power 4, L to the power 4. So we got some value 8h L by 2. It is 2 to the 4. Is it 16? Is it 16? So finally I would get a value of that t at t maximum would be equals to s times 1 root of 1 plus 16 s square by L square. So this is your standard equation for t max. So t max equals to s times root of 1 plus 16 s square by L square. So this is at x equals to L by 2. That means at the support end. From the center, here the slope was 0, here the slope is maximum. So because of that, we had tension in the cable as maximum at the support level, T max. Now one more thing is that we have a concept of cable length. We call this one as cable length. So one is your horizontal length on which your UDL was acting. This was your horizontal span of L. Now one more thing is the span, the cable length. It's along the profile itself. So this is your cable of length S. And now if I take along this profile a small segment of small length ds, such that if we approximate it to this what you call as right angle triangle of dimension ds, and this one we can say this is some dx, and this is some dy, and bottom is dx. Then we write ds is equals to root of dx square plus dy whole square. Actually it's in this fashion. Then if I convert it in terms of dy by dx, so I keep that dx common, dx whole square common, then I can write dy by dx whole square 1 plus dy by dx that whole square. And similarly, if I keep it outside end, then finally I have this equation in terms of ds equals to root of 1 plus dy by dx whole square plus into factor of that dx. Now this is your small element. If this is your small element, similarly if you want this, if you want for entire length of L, so you initially got to some value of x. There you took any element of ds. You took any element of dx such that its length along that cable profile was ds. Now similarly, if you want to take that entire cable length, so you integrate it from x equals to 0 to x equals to L, then I have this equation. I have to integrate it. Now, as per the previous problem we had in the previous lecture, that we integrated that dx also. Then we said if we ignore those upper what you call as higher order terms, when we neglect those, and I can approximately get this relation that in terms of that when I can convert it, I would write integral 0 to L in terms of this one, and this root of, I can have this function as 1 by 2 dy by dx. This is 1 by 2. This is 1 by 2. I can write it in this way. Let's have this from this part. Let's have this from this part. I want to find the total length of the cable. So for that, I took one strip small of length that ds. Now I want that total length. I want the total length. Now I would say ds. Now the total s would be equals to integral of 0 to L integral of 1 plus dy by dx whole square and integral dx. So then we say that we can if you expand it, after expanding and neglecting higher order terms, so we got the relation in terms of this one, that s is equals to 0 to L 1 plus 1 by 2 dy by dx whole this square, and this is your entire dx. This is your entire dx, yeah. Then after that we can integrate it. As we can see that cable is symmetric about the midspan. So up to the x equals to 0 to L by 2, because it's symmetric. If you talk about this one, if we get some length of S1, then we multiply it with twice, so we can get that total, that what you can call as total length of the cable. So we can change the limits such that we write 2 times 0 to L by 2 only. Now we can write 1 plus 1 by 2. What's the value of dy by dx? What's the value of dy by dx? Do you know? What's the value of dy by dx? What's the value of dy by dx? I think dy by dx was equals to 8hx by L square. 8hx by L square. Let's substitute this value. 8hx by L square. 8hx by L square. 8hx by L square. 8hx by L square whole square. Then for the entire part we had to integrate it with respect to x dx. So finally, let's solve this one. I would write 2 times. Then what is the integral of 1? What is the integral of 1 with respect to x? So I would write 1 dx integral equals to x. So finally I substitute the limits that L by 2 comma 0, L by 2 minus 0. Then plus 1 by 2 into 8 8 are 64, h square by L square. Then what's the integral x square dx? Integral x square dx, that's x square by x cube by 3. That's x cube by 3. And I substitute the limit of x cube as, I substitute the limit for x cube. I substitute this limit of x cube as L cube by 2 2s are 4 2s are 8, 2 cube minus 0. The two limits, if I have those two limits, and this 2 factor is for the entire part. And if I solve now, I would get 2 times L by 2 plus, what is this value? 2 2s are 4 2s are 8. This is 8. 8 1s are 8, 8s are 64. And can I get something cancelled here? Now I can write 8 by 3, 1 by 2, L cube. This is L cube, this is L square and L cube. So finally L and h square. We got this part. We got only this part now. So I can write, I can have this one. I can get the value that L plus 8 by 3 LH square. So I got this equation that S is equals to total length of the cable is equals to this one. Now if I simplify it once more, if I keep L common, I would get a value 1 plus 8 by 3 h square by L square. Is this what we got? I think not. I think there is some error. You check the error. Where should be the error? Function should be in terms of h square by L square. So we need to check that error. So actually the square was for the L square also. If you see that L square into that square, that is L power 4. So you had this L to the power 4, and this is L cube. So finally you got this one as h square by L. You got this one as h square by L. Now you got this as h square by L. Now if you keep that L outside, and you would get finally in terms of this equation. So S is equals to L times 1 plus 8 by 3 h square by L square. This is the cable length. This is the cable length S. S is equals to, and this is the case for symmetric cable when the load is such that it's on the horizontal, but the two supports are at the same level, such that the profile developed is symmetric with respect to the midspan. Okay, this is the length of the cable. You can't use this equation for the unsymmetric cable. There we have one more procedure. How can we get the total length of the cable? So we would be going for that. We'll take one problem for that also. So L is equals to L times 1 plus 8 by 3 h square by L square. So let's have the first problem. Let's take the first problem about symmetric. Let's take the first problem about the symmetric what you call as symmetric profile. About the symmetric profile, we have a parabolic profile. Okay, it's saying that the load is applied with the intensity of that 5 kilonewton per meter and horizontal span of 75 meter. Now because of this load, if it is saying that assume the parabolic profile, and because we say that supports are also at the same level, it's provided that supports are also at the same level. Now what you can suggest now, because of this load, it would have a profile that is symmetric about the center. Now because of that, I would say H1 would be equals to H, H2 would be equals to H. That's also equals to mid sag at the mid span. Now here the theta would be 0 at the mid span. So this is origin O, and I would say this is length L1 and this is L2. Can you tell me what is the value of L1, L2 by the symmetry? I would say this is 75 by 2. This is also 75 meter by 2. Can we say that? And it's also provided that maximum sag is 1/10th of the span. This was the problem, that maximum sag, that means H is talking about that H is 1/10th of span. So if I calculate now, what is the value of H? That is equals to 1/10th of span. Span is your 75 meter horizontal span. That means 7.5 is the maximum sag we can have. H is equals to 7.5. Now we need to get the horizontal tension and maximum tension we can have. This is the horizontal component of the tension, and this is the Tmax we can have. This is actually H square plus reaction square. Then we have for this equation that H times 1 plus 8, this is 16 times S square by L square. This is the equation for that. Now we need to get the value of H. We need to get the value of H. Can you get the value of H? Can you get the value of H? We derived one equation. We derived one equation for unsymmetric these what we call as unsymmetric profile. We derived one equation for unsymmetric profile that H1 was H was equals to where we had that one. We said that H1 is equals to H2. That H was equals to W naught L1 square by 2 H1 equals to W naught L2 square by 2 H2. We had this equation. Now for the symmetric case, if I substitute the same equation, if I said now, because we have symmetric profile, that means H1 is equals to H2 equals to H, L1 equals to L2 equals to L by 2. If I substitute here values of those, I can get the value of horizontal thrust, horizontal reaction, W naught. I substitute the value of L1 equals to L by 2 whole square divided by 2H. So I can get the value of W naught L square by 8H. Similar to that of a beam subjected to UDL, for the entire span, the bending moment maximum would be equals to WL square by 8. And if you want to calculate that horizontal reaction, then you divide by that H sag at the midspan, and you can get the value of horizontal thrust. Sorry, not thrust, horizontal reaction. H equals to WL square by 8H. So this value we can use here. We have to use this value here. WL square by 8H. WL square by 8H. So I can get the horizontal tension. I would write horizontal tension equals to WL square by 8H. Now if I substitute the values of WL square by 8H, I would say what is the intensity we can have? Intensity of 5 kilonewton per meter. Length of 75 meter whole square meter square divided by 8 into H. What is the H we have? That is 7.5 meter. So we can get the horizontal reaction. Horizontal reaction is equals to 468.75 kilonewton. Now this is also your T minimum. Can we say that this is your T minimum? Now for the T maximum, let's go for the T maximum. We write that is equals to 468.75. That's equals to 468.75 into that root of 1 plus 16 times S square by L square, S square by L square, S square by L square, H square by L square, that's 1/10 whole square. So this is our equation for that. H square by L square, yeah, 16 times. So we can have a value of T maximum equals to 504.9 kilonewton. So we got the two parts. We got the two parts of the problem. One more part is saying that get the total length of the cable. Get the total length of the cable. Yes. Get the total length of the cable. Can you get the value of total length of the cable? The relation is L times 1 plus 8 by 3 S square by L square. Now substitute the values to get the value of that total length of the cable. I would write total length is L 75 meter into 1 plus 8 by 3 S square by L square. We can write 7.5 by 75 whole square. So we got a value of 77 meter. That is 2 meter more with respect to horizontal. If this was 75 and this one is 77 meter. Okay. Let's come to the second problem. Let's come to the second problem now. It's saying that we have a footbridge of width. Footbridge is having a width of how much? 3 meter. Now it's saying that span length of the bridge, span of the bridge is what you call as 50 meter. L equals to 50 meter span length. Now if I think of that, I would say there is some horizontal length on which there is some UDL of for the length of 50 meter. There is some intensity. There might be some intensity. It's saying that we have a platform load of 5 kilonewton per meter square. That means now one more thing is provided that this bridge is supported by two cables, from both sides, from either of the sides. On one of the side we have one of the cable, and from the other side we have one of the cable, and total length we say 3 meter, and it's supporting that what you call as bridge. So that means there would be some contributing area for one of the, if you talk about one of the what you call as one of the cable takes 3 by 2 meter, and one of the cable takes other 3 by 2 meters of those width, and out of the total load of this one would get transferred to one of the cable, and rest of the load gets transferred to the other cable. Can we say that if there is some 5 kilonewton per meter square, if I want to calculate the intensity, actually this is in this way, that 5 kilonewton meter square is acting on this, that if you take one unit area, 1 meter square area, on that we have 5 kilonewton meter total loads. Total load of 5 kilonewton meter is per 1 meter square. Okay. Now if I want it in terms of UDL, I have to say how much total width is there. If I have this total width, I would say what should be the UDL we can have. I would say total intensity per meter square into total width of 3 meter. This is 3 meter. So I can get the UDL of 15 kilonewton per meter. Now this per meter means along this long line, along the longitudinal direction, along this direction of what we have total length of 50 meters span. Now if I want to convert it in terms of line diagram, now I would say your area becomes in terms of a line. Now this was your length of L. Now I want to convert it only in terms of line L. So I would say there's some UDL of total UDL of how much? 15 kilonewton per meter. Now I have to keep that also in mind, that we are not providing one cable, we are providing two cables. If we are providing two cables, that means there should be some equivalent load on one cable. What should be the equivalent load on one cable? If there's some cable between two supports, I would say out of that W dash would be equals to 15 by 2. One part of that intensity would be taken by one of the cable, and rest of that by the next cable. So I would say one of the cable is taking 15 by 2, that's 7.5 kilonewton per meter. Now this is our intensity. Let's go for the problem now. Let's take the problem now. That's easier one. That's now easy to get. Now it's saying that, what is saying? It's saying that calculate maximum pull in the cable. Calculate maximum pull. That's Tmax. Calculate maximum pull. Okay, that's saying that get the value of Tmax. For the Tmax, if the structure is symmetric, I would say that value is equals to H times 1 plus A 16 times S square by L square. So we also need that sag. What's the maximum sag we can allow that? What's the maximum sag? And that's also provided that sag is equals to centroidal sag, or we can say central dip. The central dip equals to 5 meter. Total span is 50 meter. That is 1 by 10th of the span. 5 by 5 into 10, that's 50. 1 by 10th of that span, central sag. Okay, let's calculate down. Let's calculate now. I would say T max equals to S times 1 plus 16 S square by L square. Can you get the value of H? What is the value of H? Is that also equals to W dash L square by 8H? Then we have 1 plus 16 times S square by L square. And what's the W dash we had? W dash 7.5 kilonewton per meter. So I would write 7.5 kilonewton per meter into length of L, that was 50. L was 50. L was 50. Total span length was 50. 50 meter whole square. WL square by 8H. 8 into H. Your sag is 5 meter. Into 1 plus 16 times 5 by 50 whole square. Then you can get the value of T max equals to 468.75. 468.75 kilonewton. You also can solve it by one more method, that if there's some intensity of what we had 7.5, let's say that there was some intensity of 7.5 and length was 50 meter. I would say what's the reaction we can have at this point? I would say here the theta is 0, that slope is 0. Here the slope is maximum. I would say reaction here would equals to WL by 2, vertical reaction. Similarly here, because of symmetry, reaction here would be WL by 2. If I calculate reaction, then I say reaction square plus horizontal square root, that's also T max. That way you can also get. Let's take third problem, that's unsymmetric. That's we call as unsymmetric cable. Unsymmetric cable. Unsymmetric cable. Unsymmetric cable. Unsymmetric cable. So it's giving that you have a UDL 10 kilonewton per meter, and length of that horizontal span is 100 meter. This is horizontal span. You write that horizontal span equals to 100 meter. This is the problem saying 100 meter. And okay, then one more thing is that sag of the cable measure from higher end. We have two ends. So one of the end is, let's say one of the end is here and one of the end is here. So 4 meter difference is there. Elevation difference of 4 meter. So this is 4 meter difference, elevation difference. Let's say this is some support A and support B. Now, because of the loading, there would be unsymmetric profile developed. There would be some unsymmetric profile developed. And I would say because of this one, there would be some L1, L2. Can we say that? I would say there would be some L1, L2. I would say this is some L1. From this, let's say this is some center origin O. This is L1 and this is L2. And there is some sag H1. There is some sag of H1. Here we have some sag of H2. Now, if you see the problem, what it's saying that sag of the cable measured from higher end, that's 6 meter. That means it's saying that H1 equals to 6 meter. It's also saying that sag measured from the higher end, that's 6 meter. This is 6 meter. That means if you have this reference line, I would say this is also 6 meter. This is 6 meter. And if this is 4 meter, can you get the value of H2? Can you get the value of H2? Is H2 equals to 2 meter? Can we say H2 equals to 2 meter? Okay, we got the value of H1, H2. Can we get the value of L1, L2? We had one of the equation that connects that L1 and H1. Do you know that L1 by L2 was equals to that root of H1 by H2? Do you know that? So if I use that equation, I would say L1 by L2 equals to root of H1 by H2, 6 by 2. That's root 3. That's root 3. Can we say that's root 3? That's root 3. 2 by 3, 2 by 6, that's root 3. So I would say L1 is L2 times root 3. Now if I write that total length is 100, if I write the equation that L1 plus L2 equals to 100, that means how can we get the value of L1 or L2? So I was substitute the values that L2 times root 3 plus L2 equals 100. Now I can get the value of L2 equals to 100 by 1 plus root 3. And that is 36.6. 36.6. So I got the value of 36.6. So similarly, I can get value of L1 also, that is 64.4. 63.4. So let's take one of the values, that's 36.6. To get the value of horizontal H, so we need to, the problem is saying that what we need to get horizontal tension and we need to get Tmax. So let's go for the horizontal tension. Do you know the equation that horizontal tension equals to WL1 square by 2H1? Yeah. Let's substitute in terms of L2. Let's go with respect to L2. I would say 36.6 meter. 36.6 meter. So 36.6 meter whole square, meter square. And what's the W we have? Intensity of 10 kilonewton per meter. 10 kilonewton per meter. Okay, divided by 2 into H2. What is the value of H2? 2 meter. 2 meters. So we can get the value of horizontal tension, that's equals to 3349.6 kilonewton. Now we need to get the Tmax. Can you get the value of Tmax? Can you get the value of Tmax? Can you get the value of Tmax? Can you? I think we should go. With the if I substitute that value in this way, that if I calculate the reactions, I can get the value of that R max. Out of these reactions RA and RB, I can get the value of R max. Then I can say T max would be equals to root of R max square plus S square. If I try to get the value of maximum reaction, so let's go for the calculation of reaction. Let's calculate the reactions. If I calculate the reactions, I would say let's apply summation of moments at B equals to 0. That means I would write here we have some H, here we have some A, and about the point B we had to calculate. I would say your reaction of A into length of 100 meter, total length is 100 meter. Then we have horizontal H. That is it about this point clockwise or anti-clockwise? Your point B is here and H is here, so it's trying to have a negative moment. That's anti-clockwise, so we can write negative H. We can write negative H. It should be negative H. Can it be negative H? So if I say that it should be negative, can we say that it's negative? Your A is about this point clockwise, but your H about point B, it's in the anti-clockwise direction, so it's negative. We have to keep that negative. Minus times H into your what's the perpendicular distance we have from H and B? I would say 4 meter. Can we write minus times H into 4? And we have one more load that's also anti-clockwise, that UDL effect. 10 into 100 square by 2. Okay, that equals to 0. So we get a reaction A. We know the value of H. H was equals to 3349.6. So we can get the value of A. Was equals to 634 kilonewton. And value of B is equals to accordingly, then we can write value of B would be equals to 366 kilonewton. Now, which one of these is the maximum? Your A is maximum. If I say the value of R, that T maximum would be equals to 634 kilonewton square plus your horizontal square. horizontal reaction was equals to 3349.6 square. Then root of that is T max. So that is 3409 kilonewton. This is your T max. Let's take one more problem. I would say you have loading of 7.5 kilonewton per meter. Okay. And the length of total span, horizontal length is L equals to 24, horizontal span length. Okay. Now the two supports are at different levels. One of the support is here, support A, and one of the support is somewhere here. And the difference between them, elevation difference is 4.5 meter. Elevation difference of 4.5 meter. Now because of that, we can say this is unsymmetric. The profile developed would be unsymmetric. So let's say the profile developed would be in this way. Sorry. Let's say the profile developed was in this way. Okay. Let's say the profile was developed in this way. Now, I would say there is some H1, there is some H2, there is some L1, there is some H2, L2, H1, H2, L1, L2. Can we say, okay, let's make the mahole. There's some L1, there's some L1, there's some L2. Okay, this is origin. Here the theta is 0. Okay. Now what we need to get? We need to get the cable length. Get the cable length, S, cable length. We have horizontal length of 24. We need to get the cable length of S. 24, your cable length, and horizontal tension H. Value of H and cable length. Can we write that? S is equals to L times 1 plus 8 by 3 S square by L square. Where we have derived this one? We had to derive with this one when the cable was symmetric. This was for the case of symmetric. Now, how can you get the length for this one? How can you get the length for this one? So for this one, we say, let's do one trick. How can you get the length of this one? We say, let's do one trick. Firstly, can you say what is the value of H1, H2? I would say one more data was provided that the maximum sag we have, that's equals to 6 meter horizontal sag. So that means H1 is also 6 meter, and H2 would be equals to 6 minus 4.5. That's 1.5. So we got the value of H1, H2. Now one more condition for this one. How can you get the value of S? We say you can think of these two profiles as in a way that if you have a symmetric cable, at the midspan we say that theta is 0. At the midspan we say theta is 0, and this part we say that this is some, let's say this is some L1, and we say this L1 is equals to L by 2, and from this side we say this is some L1, this is also L by 2. So we say both sides we have L by 2. Now similarly, if we say if the theta here is 0, I would say this is the peak, this is what you call as, this is a midspan of, if you imagine that there's some let's analyze that. I would say there's some cable which having some length of L1 up to the point O. After that it would have been also in this way. It would have been in this way, such that it was a beam. It was a simply support such that it was having two supports at the same level. Okay, I would say there was some length of L1 and there was some length of L1 also, such that both lengths are same. And I would say the sag here was also same, H, and sag here was also same. And similarly, I would say there was one more support, and one more beam was there, one more cable was there, such that it was somewhere here, and it developed a profile of this one up to the length of some L2. I would say this is some length of L2. And similarly, if it was continuous from the other side also, it would have been symmetric about that origin point O, and such that this one is also L by 2. And I know that for the symmetric profile, S is equals to L times 1 plus 8 by 3 S square by L square. Now, I would say for the cable 2 that was having some support of B and B, for that H there was some sag of H2. From this condition we had H2 equals to 1.5, and for the first one we had sag of H1 was equals to 6. So if I say that the cable length would be equals to the cable length, I am going to highlight it. Cable length is actually this one. Our concerned cable is only this part. This is our concerned part. So I would say our cable length is equals to 1 by 2 of that 1 by 2 of cable length. Let's say this is some cable length. Let's write in an English way. Cable length for H equals to, let's say for sag of H1. For sag of H1 equals to 6 meter, and length of, what was the length for that? Length of 2 times L1. And similarly, if I have one more, that plus cable length of with sag of cable length having sag of H2 equals to 1.5 meter, and the length is having 2 times L2. So our part would be 1 by 2 of that, sum of those two. So if I know the equation for these two, I would say 1 by 2. Your cable length for first one, what is the cable length we can have for the first one using this equation? I would say you're having a cable length of 2L1, and then we have this 1 plus 8 by 3 of S square, that is H1 square, that is H1 square by L1 square. Yeah, L1 square. That means your L1 is equals to actually 2L1 whole square. Okay. Then plus, similarly for the second case, I would say that we have a cable such that its length is 2 times L2. Then we have factor of 1 plus 8 by 3 H2 square by 2L2 square. That whole we have to divide that entire thing by we have to multiply this 1 by 2 for the entire thing, because we only need the one half of that, one half of those sum. The sum of these, we only need that part of that, 1 by 2 of that. Okay, do you got it? Now you have to substitute those values. Now before that, you need to get the value of L1, L2. How can you get the value of L1, L2? If you have the equation that, if you know the value of H1 and H2, can you get the value of L1, L2? If I say L1 by L2 equals to H1 by H2, H1 by H2, H1 by H2, is the value of H2 equals to 1.5? Yeah. So I can get the value of, this is equals to 2. This is equals to 2. So L1 equals to 2 times L2. And if I write that L1 plus L2 equals to total length of 24. Total length of 24. So I would say L2 would be equals to 8 meter. And L1 would be equals to 16 meter. Now I have to substitute these two values, 16 and 8. Now if I solve this further, I would get a value of that total length of the cable is equals to L1 plus L2 plus some 2 by 3 H1 square by L1 plus 2 by 3 H2 square by L2. This is the equation we derived finally from this one. If you simplify it, this is the equation we have. And if I substitute those values now, I would say L1 is equals to 16 meter, L2 is equals to 8 meter plus 2 by 3 of your H1 was 6 meter square divided by 16 plus 2 by 3. Your H2 was 1.5 whole square divided by L2, 8 meter. Then finally you would get a value of S is equals to 25.68. Initially the horizontal length was 24, so this one is 25.68 meter. 25.68 meter. And one more thing was to solve that, the horizontal tension H. Can you get the value of H? If you know a value of L1, I would say H equals to WL1 square by 2H1. So that's easy to calculate. What's the intensity? 7.5 kilonewton meter. Length L1 was 16 meter divided by 2 times H1, 6. So finally you would get a horizontal tension of 160 kilonewton. Horizontal tension of 160 kilonewton. Now one more thing is that we should have one more problem to take. We had to take one more problem. We had to take a few more problems. Let's go. It's saying that our central dip equals to 1/12 of span. That's h equals to 1/12 of that span L. And it's saying that get the value of L. What is the maximum length we can have? Maximum horizontal length we can have. Maximum horizontal length we can have. Span, horizontal span length. For this, we have a steel wire of some area A cross section. There's some cross section having area cross section A, okay, and with some sigma permissible values of 120 megapascal, and we have a gamma for the steel, unit weight for the steel, that is 78 kilonewton per meter cube. We need to get what should be the maximum length we can have between two supports. That L, what should be this value of L such that if you have this beam, if you have this one, what you call as, if you have a cable between these two supports hanging under the self weight, it's hanging under the self weight, then we assume that the profile developed is parabolic, and this is also symmetric. We can say this is also symmetric profile, parabolic symmetric profile. This is the solution we have. We say that under the self weight, it can have a parabolic profile, and we know that total length of the cable will be equals to L times 1 plus 8/3. Is it 8/3? Yeah, h square by L square. If I have this one, now why S is needed? How can you get this value of that? How should you get the length of L? How can you get the length of L? So we have some stresses given, that permissible stresses. So that means there should be some stress because of the load, because of some internal tension or axial tension developed. If we have some cross section A, and there's some tension developed, that T, if this is some T max, if there's some tension max and we have some cross section, we can say your T max should be such that it would cause stresses. T max should cause stresses lesser than, I would say, T max by A cross section should be lesser than permissible stresses. Can we say that? Now our stresses permissible are provided. Now we need to say what should be the value of T max and what should be the value of A. Now we need to get the equation of T max. If I get the value of T max, if our section is safe on that maximum tension, that means it's safe for all values of stresses. Because your T max is safe, that means other stresses would be lesser than that. Okay, you need to get the value of T max for this condition. And we know equation for T max. The equation for T max equals to H times 1 plus, is it 16 times? For the symmetric profile? Is it 16 times that tension? 16 times. Yeah, 1 plus 16 times. 1 plus 16 times h square by L square. Or we can also solve it in this way, that that's also h square by s square plus reaction square. S square plus reaction square. That way also we can do. We can do that way also. Now, if let's say that the loading is such that it's along the horizontal. It's along the horizontal. Let's remove this one, because we are talking about this as self weight. It's not along the horizontal. It's along the profile itself. It's along the profile. Can you tell me what's the total weight of the cable? Can you tell me what's the total weight of the cable? If I'm able to get, because there is no external load, the total load is under because of the self weight. We need to get the value of self weight. What is the total weight of the cable itself? So if I say what's the total weight of the what's the total weight of the cable, I would say total weight of the cable is equals to gamma times volume, gamma into volume. So there is some 78 kilonewton per meter cube, and there is some area cross section A, and there is some cable length S. There's some length of cable S, not L. This is because weight is along the cable length, so that's S. So So for that, we needed this value of S. And from this S, we have function of L. So your value of L is unknown, so maybe we can get the value of L accordingly. So if I have this equation in terms of that S is equals to function of L, and we can finally, we might get value of that, we can see what we call as value of L. So let's keep that W in terms of that gamma into AS. Okay. Now I would say for the T max, I would say you have horizontal direction of H, and we have some vertical direction of R. Can you tell me what is the horizontal we can have when the beam is symmetric, when the loading is when the supports are at the same level? What is the horizontal direction we get? What is the horizontal direction we get? Is that WL square by 8H? Is that equals to WL square by 8H? Is that equals to WL square by 8H? Now, if I say what's W, it's in kilonewton per meter. But if I say what is the total weight along the length, if I say what is W into L, that's total weight of W. That's total weight of W. That's total weight of W. So that means if I substitute that value, I would say W into L equals to W, total weight of W. So I would write that H equals to W L by 8H. And I have the value of H also, that H is equals to 1/12 of the span. So H is equals to 1/12 of the span. WL by 8, 1/12 of the span L. So finally I would get 3/2 of W. So H is equals to 1.5 W. And similarly, I can get the T max. I can get the reaction also. Can you get the reaction if we have two supports and loaded symmetrically? I would say the reaction 1 would be equals to reaction 2. What is the reaction we can have? R. Would that be equals to total weight? Has to be, because total weight is always downwards under the action of gravity. So 1/2 of that load would be taken by one of the reactions, W/2. Now if I write that T max, if I solve now T max, I would say 3/2 of W whole square plus W/2 whole square and T and root of that, so we can get T max. T max equals to some value of 1.581 W. So this is one approach. Second approach, I said that you can solve it by this equation we derived. If you use this equation also, I would say T max would be equals to, now for that you need to get the value of H. So initially you need to get the value of H. So let's say H was equals to 3/2 of W. Then we have to that factor of 1 plus 16 times H square by L square. What is the H value in terms of L? 1/12 of that. So 1/12 of that, I would write 16 times 1/12 of that. That's 1/144. So finally you can have that value, same value of 1.581 W. I got this total weight of 1.581 W. If I divide this by cross-section area A, I can get the stress. So I would say that T max by A cross-section, that is some stress, and this should be less than or equal to sigma permissible. This should be equal to less or equal to this should be lesser than or equal to permissible stress. So T max was equals to 1.581 W. 1.581 W divided by A, that should be less than or equal to sigma permissible, 120 megapascal. 120 megapascal. This is our equation that we derived. Now I need to say what's the value of weight. What's the weight? Self weight is that gamma AS, gamma into AS. So I have to get the value of gamma into AS. Let's write that gamma into AS. I would say gamma AS into this factor of 1.581 divided by area A. This should be, let's equate now this with the 120 megapascal. Okay. Now our area goes cancelled. Area gets cancelled. So what we need to convert that cable length into total, that horizontal length S. So if I write that cable length in terms of horizontal length, so that's L times 1 plus 8/3, 1/144. So that's some value of S is equal to some value of we can directly now write that. We know that gamma is 78 kilonewton per meter cube, and value of S was comes out to be equals to 1.0185 L. This is the value of S. And after that, we have this factor of 1.581. And this should be equals to 120 megapascal. And you would get a value of L equals to, L should be equals to 955.45 meter. Under the self weight, it can have between the two supports, it can take up to this length. That means cable should be such that we can have a horizontal span of even a horizontal span of 955.45 under the self weight. Okay. Let's pause. So let's come to our one more problem. Let's come to one more problem that we have, that you have a UDL 2 kilonewton per meter, span, horizontal span 60 meter, two supports at elevation difference of 5 meter, such that sag at one support is 10 meter. Let's write it in one more way. Sag is in this way, sorry. Let's say that the sag H1, let's say this is some sag H1, this is equals to 10 meter, and from this side we have sag of H2 that equals to 5 meter. That means elevation difference was initially 5 meter. Now we have these two supports, support A, support B, and the horizontal span we have 60 meter with UDL acting with 2 kilonewton per meter, and you need to get the horizontal tension. Is it easy? Can you do that? For the horizontal tension, we have the equation that WL1 squared by 2 H1 equals to WL2 squared by 2 H2. You can solve for either of the side. So for that, you need to get the value of L1, L2. So let's say the origin is here. I would say this is L1, this is L2. And I have the equation that L1 by L2 equals to root of H1 by H2, that is root 2. I would say that means total length is 60, so I would write that root 2 times L2 plus L2 equals to 60. L2 equals to 24.85 meter. So let's keep in terms of L2. I would use that equation. In terms of L2, I would say H equals to 2 kilonewton per meter into length of L2, 24.85 square meter square, divided by 2 times H2, we need to get the H2. The value of H2 is 5 meter, and you can get the horizontal tension equals to 123.53 kilonewton. Let's come to one more problem. That's a cable subject to concentrated loads. Let's say because of the loads, profile is in this fashion. Let's say because of the loads, profile developed was in this fashion. Okay, now we are applying loads. One of the load is 15 kilonewton, and one more load is 30 kilonewton. Let's call this support as B. Let's say this support is A. We might be having some reactions here, and I would say they are at the same level, and I would say this is 4 meter. Total length is 12 meter horizontal, so that means this is 4, and this is 4. Now we need to get the value of H, that is the horizontal reaction, and we need to get the total length of the cable. Total cable length. So let's say that this point is C, this is D. So we need to get the length of LA CDE, let LACDB, LACDB. Yeah, we need to get this length, and that is equals to LAC plus LCD plus LDB. And one more data is provided that the sag here at this point, the sag is equals to 1.5 meter. 1.5 meter. Do you know the general cable theorem? Do you remember that general cable theorem? What was the statement of that? Was this the statement of that cable, of that theorem? Is this the statement of general cable theorem? That horizontal reaction into a y ordinate at any location x in the cable is equals to bending moment at that section x in the simply support beam. Now, if I write that, what is the now how to get the horizontal reaction? Horizontal reaction can be solved if I say both supports are at the same level, then if you apply that summation of moments about point B, in that there won't be any reaction horizontal, that its effective would be 0, so you can't get the equation of H in this way. So you need to cut the section somewhere such that you would get a reaction of H. So you need to cut some section at any x at any section x such that you would get the such that after that you can have the horizontal reaction H. So for that, let's say that for the horizontal reaction, I am going to cut any section such that I have the data known to me. I have the y data known to me. Out of these two, where should be the feasible location that you can cut the section where you know the effect of that H into some y ordinate. I think the data provided is that at D you have a y ordinate of 1.5 meter. So you can prefer that one. You can prefer that one. So if I take this section, I would say here the horizontal, here we have two reactions. One is your horizontal, one you have reaction B, and the horizontal distance is 4 meter, and the vertical is 1.5 meter on this section. And we know that in the cable, bending moment at any section is equals to 0. If you solve it, I would say let's apply that summation of moments at that section O, at that section moment at D, at this section D. If you say summation of moments at D equals to 0, I would write H clockwise about this point O, H into 1.5 equals to B anti-clockwise into 4. So I got the relation between H and B. So I have to get the value of B. So that value of B can be solved if I take that summation of moments about point A. If I take summation of moments about point A, I might get the reaction B. Let us go for summation of moments at A equals to 0. I would say your reaction B about the point A, it's having anti-clockwise. So if I write minus times B into total length was 4, that's 12, and that's anti-clockwise. And all other loads are clockwise. That is 15 into 4 clockwise plus 30 into 8 clockwise equals to 0. So reaction B was equals to 25 kilonewton. 25 kilonewton. And reaction A we also can solve. That is 25 minus 45. That's 20 kilonewton. 20 kilonewton. So we got the reaction B 25 kilonewton. 25. If I substitute here 25 into 4 divided by 1.5 is your horizontal component. So that value equals to 66.67 kilonewton. 66.67 kilonewton. Now I got the one of the part of the problem, that is H. Now we need to get the total length of the cable. And to get the total length of cable, I can use those rectangles. I can use Pythagoras sum. I would say this length. If I say what is the total length, that AC, can you tell me what is the AC? I would say AC is equals to 4 meters square plus some vertical here, YC square. Similarly, we can write CD. CD is equals to, we have one more rectangle here, and the vertical ordinate is equals to 1.5 minus yc whole square plus horizontal is 4 meter whole square, then we do root, and one more length is there, we can say that's bd, I would say bd equals to root of 4 meter square horizontal plus one more thing, that's vertical 1.5, then we can get the values. Finally, I would do summation of all those values. Then so for that, initially we need yc value. So for getting the value of yc, I have to use this cable theorem. If I take that section, add this section, if I cut this section AC, I would say here the moment would be 0, bending moment. I would say here we have reaction of H, and we have some reaction of A, and there is no any other load just before section C. I would say your A into horizontal of 4 is balanced by H into vertical of YC. So I can get the value of YC. Equals to A. What's the value of A? We got. What is the value of A we got? Can you tell me what is the value of A we got? What was that one? Yeah, value of A was 20 kilonewton. 20 kilonewton into 4 meter divided by horizontal. Horizontal reaction was 66.67 kilonewton. 66.67 kilonewton. So I can get the YC ordinate as that is equals to 1.2 meter. Now I can get the total length. I can get now total length of the cable. I would say that some 1.2 is there, 1.2 square, 4 square plus 1.2 square, and this is 1.5 minus 1.2, that is 0.3 whole square plus 4 square, and this one, if I say AC plus CD plus BD, and I can get the value of that total length of the cable. We can write L of the cable is equals to, that comes out to be equals to 12.45 meter. This is the total length of the cable. Now we are coming for the next, that's the last topic of the cables we have. This is the final topic for the cables, and it's called that influence of those factors. That's how some factors influence of, we have these factors, then we see the influence of these. Let's try that. It's for symmetric parabolic profile. It's for parabolic profile, and that too if the profile is symmetric. So we have derived those value equations only for the symmetric profile, because that is easy to derive. When it is symmetric, the conditions become easier. So we say we have derived these values for the parabolic symmetric profile. Let's have that. That means when loading is in this way and supports are at the same level, then let's go for that. We need to say number one is that influence of elastic stretch. So we see what is the influence of elastic stretch. What does that mean? We say our assumption was that cable is actually inextensible. We say that your assumption B was cable is inextensible. This was the assumption we said. But if we analyze that, if you see in the real world, we say no material is ideally rigid. No material is actually rigid. That means if you apply some load on a cable, there would be definitely some axial deformations. And if you calculate for this, what you call as for the cable, symmetric cable with the parabolic profile, the equation for that is how much change is in there. I would say delta in the cable, delta in the length of the cable. That is, we are talking about the cable length in this way. That means once there was some tensile force, so its length initially was S, and there would be some increase in the length by some delta S, that is the increase in length. So this is the, we can say, this is the increase in length, delta S, because of elastic stretch. Let's write it as delta SE because of elastic stretch. So that is equals to PL by AE. Similarly, we have HL by AE, and you have some factor. You have some factor of 1 plus 16 by 3 h square by L square. Okay, this is the equation we have. If the cable is parabolic symmetric. This is the equation, right? Equation number 1. One more is the effect that influence of temperature. Now, because of temperature change, let's say because of temperature change, we know that delta equals to alpha LT. This is T is the increase in temperature or change in temperature. Similarly, if you have a cable of cable length S, and the material is having some alpha coefficient of thermal expansion, and there is some temperature change alpha ST, I can say delta change in the length of the cable is equals to delta S. Let's write that delta ST, change in length of the cable because of temperature change, that is alpha ST. And if I substitute the value of S for the case of hinged symmetric profile, for the case of parabolic symmetric profile, what's the equation for that? I would say delta ST is equals to alpha times L into 1 plus 8 by 3 h square by L square into temperature of T, change in temperature of T. Do you have this one? So delta ST equals to alpha times L 1 plus 8 by 3 h square by L square into delta T, change in temperature. Now, we can say this is the direct relation. If your temperature got increased, that means your expansion would get, that means cable would get increased, cable length would get increased. Okay, one more topic is that change in sag due to change in length. One more effect is that change in length. This is the third case that we say change in length. What is the change in length? That's your change in length. That is how much change is in the length of the cable. That is S. Let's say some change dou S. Let's say represent it by dou S. But because of change in length of the cable. Yeah. This is actually change in sag due to change in length. Topic is actually in this way. Change in sag. So that is dou H because of change in length. Because of change in length, there is some change of sag. If I have that equation, that cable length equals to S times 1 plus S equals to L times 1 plus 8 by 3 h square by L square. If I differentiate it, I would say dou S is equals to change in length equals to L times 0 plus 8 by 3. If I differentiate this sag also, I would say 2 times H. I would say 2 times H and some dou H, change in H divided by L square. So I can have some equation of that change in length. Because of the change in length, we have change in sag. So I would write that is 8 to the 16 by 3 H by L square and dou H. So if I would say, what is the change in sag? I would say change in sag is equals to 3 times L square by 16 and change in length. So this is the result we have. So change in sag equals to 3 by 16 L by, this should be, yeah, we had this factor that this was your L and we have this L square, and finally it would become L. So this is the equation, that L, and H was also there, L by H. So this is the result we have. This is the result of that change in sag. So this is change in sag, that equals to 3 by 16 length by sag, initial sag, into change in length. This change in length, we say this change in length can be either contributed by elastic stretch, or it can be because of temperature change. It can be because of elastic stretch, or it can be because of temperature change. So this delta S. So now one more topic is that, one more thing is that change in cable tension due to sag. Change in cable tension due to sag. Change in cables. This is the fourth case of this. Change in cable tension because of sag. Change in cable tension due to sag. Due to sag. So because of some sag, because of some change was in the sag was there, you can say that because of change in sag. So I would say because of some change in sag dou H, you had some change in tension dou T. Change in cable tension because of change in sag, or we can say dou H, while H is also tension in the cable. This is minimum tension. So I would say if I have the equation that H equals to WL square by 8H, this is all these data we are deriving for the parabolic symmetric profile. You have to ensure that the profile is parabolic profile. This equation is valid for a symmetric profile, that when the UDL was acting and the two supports were at the same level, such that the profile developed was parabolic symmetric profile. And for that we have H equals to WL square by 8H. And if I differentiate it, let's differentiate it. I would say dou H equals to WL square by 8, and differentiation of 1 by H is minus 1 by H square into some internal differentiation dou H. So this is your differentiation for this one. And I would say I would convert it in terms of let's write what is the value. If I substitute the value of H again back, I would say there is some value of WL square by 8H, and there is some value of minus dou H by H, and I would say this is some value of H minus dou H by H. Can we say it? Can we say this one? And if I convert it in this way, I would say dou H by H equals to minus times dou H by H. This is the result we got. That change in what you call as change in horizontal tension with respect to the horizontal reaction we have, that is equals to minus times change in sag with respect to the original sag. So that means if your sag is increasing, that means if the sag your sag got increased. If initially sag was 5 meter, now if your sag was such that it got increased to 5.1 meter, that means your horizontal reaction would get decreased. So this would get decreased. So there is inverse relation. Now one more thing is that we can convert it in terms of the thing in terms of the tension also. We have the equation that tension is equals to H square plus T square with the root. And I would say that T, if I say this is the T max reaction, I would say this is the T max. If I say T max square equals to H square plus reaction square, what is the value of H we have? That is WL square by 8H. And we have this reaction of, what is the reaction we can have? Maximum reaction we can have. For the T max, what should be the reaction? That means at the support, at the location of support, here the tension would be maximum, because here the reaction is maximum, and that maximum reaction is equals to WL by 2. WL by 2. WL by 2. WL by 2. Now we see that because your R is not a function of, it's not a function of H. So this topic is that a change in sag, because your reaction R is not a vertical reaction, is not a function of H. It's only a function of that total UDL. That's not going to change. Total length is not going to change. Horizontal span. You have two supports. They are not going anywhere. That means L is also fixed. UDL is also fixed intensity. Only the sag of the profile is getting changed. Either it can shorten, it can come back, it can elongate more, it can have more sag, it can have lesser sag. So these things are going to change. Because of that, we can change the horizontal reaction, and because of the horizontal we can change the T max. So we say because of the sag your Tmax is a function of h only. So if I differentiate it with respect to that, I would say 2 times Tmax, and there's some change of T dou Tmax. That's only a function of h. So I would say, you can see from this one that capital H is a function of that sag only. Capital H only is a function of sag. R is not a function of sag. So that part would become 0. If I write that, I would say 2 times h and dou h, and plus I would write this one as 0. There's no change with respect to sag. So I would say I would get a result that Tmax dou Tmax equals to h dou h. And if I say what is the value of dou Tmax we can have, I would be saying that equals to h times h by Tmax and dou h. Yeah, this is the capital H, capital dou h. That capital dou h, that is change in horizontal direction. So this is the equation we derived. This is the equation we derived. We say that your dou h is equals to, we already derived what was the value of dou h. That was equals to h times dou small h by that initial h minus times. So since we say h is a function of minus times h dou h, that means your horizontal direction decreases as the h increases. And similarly, I would say because that change in t is a function of h, I would say that's a function of dou h. And if this goes decreasing, this is also going to decrease. And we can draw one conclusion that this is very important. You can remember that one. I would say increase in length, because of increase in length of the cable, because of increase of length of the cable by some delta s, we have increase of sag. We derived the equation for that also. We have the increase of sag. You have the equation for that. Because of the increase of what you call as change in cable length, we have that increase of that sag also. So they are directly related. So by increasing the cable length, our sag also increases. That is obvious. That's obvious. If you have two supports, they are not going anywhere. If your length is going to increase, and more sag would get developed. Okay. Increase in length of cable by some delta s, we can have increase of sag, and by that we can have which would indirectly say your h and t also gets decreased. There is dou h and dou t, they got decreases such that final h final is lesser and t final is also lesser. We can say that also. Now we can take one problem such that our concept gets stronger and stronger. Let's go for that. Let's take that case. It's saying that we have that 5 kilonewton per meter acting for the horizontal span for the length of 75. So L is equals to 75, and we have two supports. That means the supports are such that they are at the same level. So the profile would be parabolic symmetric profile. And for that, sag at midspan is maximum. So we know that h equals to WL squared by 8h. So what is the data we need to get? It's saying that h at the midspan, that central sag equals to 7.5 meter. Okay. What's the data that's provided? It said that alpha equals to 10 to the power minus 5 per degree Celsius, and modulus of elasticity for the material, that's maybe steel, 2 into 10 to the power 5 megapascal, and we have area cross section of the wire of the cable, that's equals to 500 millimeters square. So this is the data provided. Now we need to get, we have two cases of the problem. First case is that find the percentage reduction in Tmax. Find the percentage reduction in Tmax because of first case is that because of elastic stretch. And second case is that because of what you call as temperature change 30 degrees Celsius. Let's say 30 degrees Celsius increase. Let's take 30 degrees Celsius increase. Now let's go for the first case. Now because of elastic stretch, we say your cable length would get increased, and because of cable length gets increased, sag would get increased, and because of sag, horizontal reaction gets decreased, and because of horizontal reaction, your Tmax gets reduced. So this is the profile of the solution. So let's go for the solution now. I would say, what is the elastic stretch we have because of what's the change in length because of the elastic stretch? Do you know the equation? We have that equation, that PL by AE, that's HL by AE with some factor of 1 plus 16 by 3 H square by L square. You have to just substitute those values, and firstly you need to get the value of H. Can you get the value of H for this problem? I would say H equals to W L square by 8H, and we can have H equals to, the value of H equals to 468.75 kilonewton. And can you get the value of Tmax also? Can you get the value of Tmax also? Tmax is equals to that you can directly get. Let's say the value we already know, that's S square plus WL by 2 whole square, or we can say H times 1 plus 8 by 3 of S square by L square, or 16 times. Is it 16 times? I think the equation we know that we directly can solve for that. So let's say that T is also known to us, H is also known to us, and S, total S is also known to us by the equation of parabolic equation we know. That's 77. Let's say this is 77 meter. We have one of the problems that was based on this one. You can check that. We have solved this. These results are from the previous problem we had on the symmetric profile. The data is taken as it is. Now we need these. We know these two data. Let's take the value of H, 468.75. 468.75 kilonewton into total length of 75 meter, divided by area cross section was provided to you 500 millimeter square, into modulus of elasticity was 2 into 10 to the power 5 megapascal, and 1 plus 16 by 3 of H square by L square. Your H is 1 by 10th of the length, so I can directly write 1 by 100. Can we write directly 1 by 100? So finally we can have change in length because of that elastic stretch, that equals to 370.3 millimeter. And now because of delta S, because of change in length of the cable, we have change in length of the change in the sag, that is equals to dou H, and that is equals to we have that equation of dou H equals to 3 by 16 L by H and dou S. Now let's write those values. L by H, what do you know the value of L by H? Is that 10? 75 by 7.5, and we can have dou S equals to 370.3 millimeter, and that value is coming out to be 694.3 millimeter. Once we got the dou H, we can get the change in horizontal. So I would say dou horizontal equals to minus times horizontal into dou horizontal by horizontal. Sorry, dou sag by sag. So we can say, what is this value? Change in horizontal. That is minus times the horizontal reaction, 468.75 kilonewton, into change in sag, that is 694.3 millimeter. What was the initial sag we had? That was 7.5 meter. 7.5 meters. That is 7500 millimeter. And we can have change in horizontal, that's equals to minus times 43.39 kilonewton. And because of this one, can you get the change in tension? Dou Tmax equals to I think that was in divide. Dou Tmax. Now we need this equation. We have to get a percentage in terms with respect to Tmax. We solve it in this way, that dou Tmax by Tmax, that is equals to, this is the percentage reduction. We are going to solve in this way, percentage reduction into 100. Now for that we need to get the value of dou T max. Dou T max. We have the equation dou T max equals to dou H and H by dou T. Do we have that equation? Let's write that now directly. I would say this is the equation for change in maximum tension. Dou T max equals to dou H into H by dou T. Sorry, this is bottom should be, denominator should be T max here. And from the previous result we have the value of T max also 504.9. 504.9. I can write 504.9 kilonewton. And we have the change of horizontal, that was minus 43.39 kilonewton. And what was the initial horizontal reaction? 468.75. 468.75 kilonewton. So change in T max is equals to 40.28 kilonewton. 40.28 kilonewton. So that is also negative, you can say. And finally, I would say, what is the change, percentage reduction or percentage change in the T max? That is minus 40.28 kilonewton divided by initial value of 504.29 into 100, and that's some percentage of 7.97% reduction because of increase of sag, and because of increase of length, your horizontal, that tension T max got reduced by 7.97%. Okay. Now second part of the problem was because of the temperature change, you need to get the percentage reduction because of temperature change of 30 degrees. So I can solve that. I would say delta ST equals to, I would say delta S because of temperature change, that is equals to alpha times initial length of the cable, initial cable length into temperature change of 30 degrees. So I have to use those values, alpha 10 to the power minus 5 per degrees. So I would be writing that 10 to the power 5 minus 5 per degree Celsius into cable length was calculated as 77 meter into 30 degrees Celsius. You can get the delta ST, that is equals to 23.1 millimeter. 23.1 millimeter. Okay, and because of that, let's remove this one. This part we have to remove. And because of that, dou S, let's write this one as dou S because of temperature change. This value we have to substitute as the value we got 23.1, and because of that we would be getting some result of change in sag. Change in sag equals to 43.31 millimeter. 43.31 millimeter. And because of that change in sag, I would substitute that value here, 43.31 millimeter. Because of that, I would get a change of horizontal tension as negative times this value comes out to be equals to minus 2.71 kilonewton. And based on the change of horizontal tension, we say the change in T max would be that this value we have to substitute here. That in place of this one, we have to substitute minus times 2.71 kilonewton. Okay, we substitute this value now, and the rest of the parts are same. Now we got the value of T max change. T max is equals to negative times dou T max equals to minus times 2.5160 kilonewton. Now I would say, what's the percentage reduction? I would say 2.5160 divided by initial value of 504.29. So you would get a value of percentage decrease of how much percentage? 0.4983 percentage. So that we can say, because of elastic stretch, there is a more change in that length. There is more change in tension because there is more change in cable length. So based on that, we say that your tension T max also gets reduced. Now one of the final problems we have, then we can have the blank page. That is the final problem we have for the cables. It's saying that we have a 30 kilonewton per meter UDL for the 60 meter span, horizontal span of 60 meter. Okay, with a central sag of 6 meter, alpha 12 into 10 to the power minus 6 per degree Celsius, And what we need to get, it's saying that temperature falls by 30 degrees. Okay, now we need to get percentage increase of horizontal tension. That means it's saying that percentage horizontal tension dou h by h into 100. You have to solve this percentage increase of horizontal tension. So we say because of the temperature fall, your length of the cable would get shortened, and because of the cable got shortened, your sag got shortened, and because of the sag got shortened, your horizontal would get increased. Horizontal reaction gets increased. So that's the profile of the solution. Let's go step by step. I would say calculate the delta S because of T. So that is equals to alpha ST. Let's go for that. I would say your value of alpha was 12 into 10 power minus 6. Let's use those values. 12 into 10 power minus 6 per degree Celsius. And what is the cable length S? Can you get the value of S? I would say if you have two supports at the same level, the value of cable length would be equals to 60 meter 1 plus 8 by 3 6 square by 60 square. Can you say that? And that value equals to S is equals to some value is there. S is equals to that would be greater than 60 meters. So let's have some value of S. Some meter is there, and you multiply with that. Because your temperature is decreasing, falls by 30 degrees, so we had to write minus 30. So that means your length gets shortened. Cable length would get shortened. So that value is minus times delta ST equals to minus times 22 millimeter. So based on this 22 millimeter, I would say there would be some change in sag. Dou H would be equals to 3 by 18. Is it 3 by 16? Yeah, 3 by 16. Change in S. This is change in S. Yeah, equation is L by H, change in sag, change in this what you call as because of delta ST. I would say delta ST. That is the equation for this one. So I would say 3 by 16. Total length was 60 and H was 6. So that's, we can say 10. 60 meter by 6 meter. And delta ST was minus times 22 millimeter. So we can get the change in sag is, that is negative, that is degrees of sag is equals to 41.25 millimeter. And now we can say what is the decrease of, how much decrease has occurred in the horizontal reaction. I would say that is equals to dou H, and that equals to, I would say dou H by H equals to minus times dou small h by small h. And we need to get the value of H first, or we can directly say this value is the percentage increase of tension. We don't have to get the reaction H. We can directly write this is the percentage increase. Now if I say we got this value of that dou H as minus 41.25, let's use that value as minus times minus 41.25 millimeter, and initial sag was 5. Initial sag was 6 meter. So initial sag was 6,000 millimeter. 6,000 millimeter. So you got this value. If I multiply it with 100, that would give me percentage increase of horizontal tension. If I multiply it with 100 from this side also, if I multiply it with 100, you would get a percentage increase of 0.687 percentage increase. So this percentage of increase is there. So final thing is that you have to remember that by increase of cable length by some delta S or dou S, there was some sag increase. Dou H sag increased. So sag increased, and because of that your horizontal tension and Tmax they got reduced, and vice versa. You can say vice versa. Okay, thank you for watching this cables. So this is the end of the cables. Thank you. Okay, thank you.